Welcome back. In this video, we're going to start exploring the concept of the definite integral. With definite integral, what it's going to do is you're going to be looking for the value of the integral on a particular interval from a to b. A and b become what we call our limits of integration. The f of x dx is still the integrand and all that stuff. And what the integral does is it takes the area that is bound by the graph and then the x-axis, and it finds this area, and if the area is above the x-axis, it's considered positive. If the area is below the x-axis, it's considered negative. So that's why this is a positive, this is a negative, so on and so forth. What we do is we'll eventually get to what we call the fundamental theorem of calculus, which will find that area exactly. But in this first video, what we're going to explore is the concept of what we call Riemann sum. And the Riemann sum is named after the person who developed it. And what he did was he said, okay, well, we can draw rectangles and other geometry shapes below the axes or below the curve, and we can estimate the area of those rectangles, and that will give us the area and based on the graph. And so there's three different techniques. There's called a left-hand sum, which uses our left, like in these particular examples, we have each of these rectangles with equal widths. And on this first one, we use a left-hand sum where I go up to the graph on the left-hand side and I go over and I go back down. And that gives me the height of the rectangle. The delta x is the width of the rectangle. These ones are shown as delta x being the same, although sometimes they can be different. In a right-hand sum, you start on the right-hand side of the interval, you go up until you hit the graph, and then you go over. This would be a slight overestimate. This would be a slight underestimate. That's because the graph is increasing. And then we would, if you use the midpoint, you just use the midpoint of the interval to give the approximation or to give the approximate height. There's also another technique, and that's called trapezoidal rule. And with the trapezoidal rule, what we're doing is we're drawing trapezoids underneath the graph, and we're just finding the area of each of these trapezoids individually. And the trapezoid is going to be an overestimate or underestimate based upon the concavity of the graph. Graph is concave down, it's going to be an underestimate. Graph is concave up, it's going to be an overestimate. A couple of examples. This first one, I'm going to approximate this integral of 2x minus 1, which is just a line between 1 and 4. And so what I did is I draw the line, I draw my rectangles. I'm using my left endpoint approximation, and I'm using 6 rectangles. And when I did that, what would happen is I want to find delta x. I want to find out how much I'm going up by. In this case, they're all equal width. So delta x would be the upper limit 4 minus the lower limit 1 divided by the number of rectangles, which is 6. So I'm going up by 1/2. And then when I find the area for this, what I'm going to do is I'm going to pull that 1/2 out front. And then the left endpoint approximation, I'm just going to add up all the heights. Well, my first height starts down here at f of 1 and then goes over 1/2. And then my next height goes to f 1.5, and so on and so forth. I'm going to have all these different heights. I'm not going to include f of 4 because that's not a height of my rectangle. So it's going to be f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. If you look at that, that gives us 6 heights. 1, 2, 3, 4, 5, 6. 6 different heights. I multiply it by 1/2. The rest of it's just kind of number crunching. I found that area to be about 10.5 units, whatever units may be. I'm going to do a right endpoint approximation, and this one I changed my graph to x squared, and now I start on the right-hand side of the interval. I'm approximating the value between 0 and 3, and I'm just going to use 3 rectangles. And I'm starting on the right-hand value, so this is going to be f of 3, and then f of 2, and then f of 1, and those are going to be the heights of my rectangle. So again, my delta x is going to be 3 minus 0 divided by the number of subdivisions, which is 3. So it's going to go up by 1. So 1 out front. And then my heights this time, I'm going to start on the right-hand side of the interval because I'm using right endpoint approximation. So it's going to be f of 3 plus f of 2 plus f of 1. I'm going up and down by delta x when I'm in finding my heights. When I did that, I found that to be about 14 in this particular example. And then if I go to my midpoint approximation, and my midpoint approximation, again, I change the graph. I'm going between 0 and 2, and I'm changing it to 6 minus 2x. Again, just a line. And this time I'm going to approximate it by using 4 rectangles. So that means each of these rectangles are going to be 1/2 of a unit wide. And then what I'm going to do is I'm going to use the midpoint of that interval to find the height of the rectangle. So my delta x this time is going to be 2 minus 0 divided by 4 rectangles, which is going to be 1/2. So 1/2 out front. And then I'm going to use the midpoint on each interval. So on this first interval, it's going to be 0 up to 0.5. So the midpoint is 0.25. So I'm going to calculate what is f of 0.25. And then the next one is going to be f of 0.75. And then f of 1.25. And then f of 1.75. I did that and I calculated, I got 8.5 when I worked all that out. And then my other geometry approximation is my trapezoid rule. Again, this one, I didn't draw a picture of this one, but I'm going from 0 to 4 of x squared minus 1. The area of a trapezoid is 1/2 of the height times base 1 plus base 2. In my example, this height is going to be delta x, and since I'm using 4 trapezoids of equal width, I've got to find delta x. My delta x value, how much I'm going up by, is going to be 4 minus 0, my limits, over the number of rectangles, which is 4. So it's just each one's going to go up by 1. So it's going to be a 1/2, that's from that formula, times the height, which is 1. And then I've got to add up those base 1 plus base 2 and so on and so forth. Those are going to be my f of x values. The first one I'm going to find is f of 0. And that's just the part of the first trapezoid on the far left. And then the next one is going to be f of 1. I'm going to multiply that by 2 because it's going to be part of 2 different trapezoids. And then 2 times f of 2, again, part of 2 trapezoids, plus 2 times f of 3, plus just f of 4. That last trapezoid is only going to have, I'm only going to count that height one time because it's just the far right boundary. When I worked that out, I got 18. What happens in these problems, if you have nice equal widths, you can write out these formulas, but oftentimes they don't have equal widths, or they give you the table, they give you the values in table as opposed to an equation, and then you just have to estimate it by using the different intervals. So this first one is a left-hand sum, 4 intervals based on this table. Now again, each one of them is going up by 1, so I can pull a 1 out front, and then my heights are going to be left-hand sides, so 1 height, 2 height, 3 height, 4 height. I don't include the 3. So 20 plus 18 plus 17 plus 11. And then I multiply that by 1. And when I did that, I got 66. If you do it as a table, and I'm using my right endpoint approximation, oh, excuse me, not right endpoint, this one's a midpoint approximation with 3 subintervals. So my intervals are going to go from -1 to 0. That's 1 unit wide, and my height's going to be 30. So it's going to be, again, 1 unit wide, my height's 30. And then the next one's going to go from 0 to 1, the height's going to be 19, the midpoint of the interval. And then finally, the last one goes from 1 to 2, and the height is 15. So this ended up being 64. Again, our delta x was equal, so we can just work that out. Now in this one, finally, delta x is not equal. Since delta x is not equal, I'm going to use a trapezoidal sum, and I'm going to use 3 subintervals. So I just find the area of each trapezoid individually. It's going to be 1/2. Now delta x is the height, so that's going to be 3, times the sum of the bases, which would be 2 plus 5. And then the next one would be 1/2. The next trapezoid between 3 and 4, so the height is 1. The sum of the bases is 5 plus 7. And then plus 1/2. The delta x would be 4. And then the sum of the bases would be 7 plus 11. Again, just crunching numbers, calculating it out, and I got 52.5. All right. So just finding area using geometry formulas. I'll clarify in class the best I possibly can. See you soon.